We did the ice cream cone in rectangular coordinates in our last set of videos for section 16.4. I want to do it again now in cylindrical because it's actually easier in cylindrical coordinates. We're actually going to do it again in spherical coordinates next to show you the full kind of range of possibilities on one of these problems. But what we have here is a cone, right? Z squared equals x squared plus y squared. This is the upper half of an elliptical cone. And then this is an ellipsoid. If you square both sides, you have z squared equals plus x squared plus y squared equals 4. So actually a sphere, not just an ellipsoid, because the coefficients are all the same. So it happens to actually be a sphere in this case. So a cone and a, let's draw a sphere centered at the origin is going to look like that, and a cone is going to look like this. So what we're dealing with is that ice cream cone shape. That's the intersection of the two things here. So we have the sphere, we have the cone, we're dealing with that shape, which I've been calling an ice cream cone. You won't find that in the textbook. And that's it. So we want to integrate over that region. Now we're looking for a volume. That means we're integrating the function 1. So we're going to integrate 1. And we know we're going to have an r dz dr d theta when we do this in cylindrical coordinates. We have that extra r in there, and the dz dr d theta. And what do we have? Well, z is going from the cone below, right? If we think the cone is on the bottom here, up to the surface of the sphere on top. So z goes from the cone below, and z is the square root of x squared plus y squared. In cylindrical coordinates, that's r, because r squared is x squared plus y squared. So z is r, and it's going up to the square root of 4 minus r squared up above. It's going from the cone below up to the surface of the sphere above. Now we have to figure out the bounds for r and theta. To do that, right, we got to figure out what this intersection between the cone and the sphere is. And so the intersection, we did this previously in a couple of problems. We set the surfaces equal to each other. So we have the square root of 4 minus r squared. That's the sphere. And we have r, which is the cone. And square both sides. That's 4 minus r squared equals r squared. That means 2r squared equals 4. So r squared equals 2. So r equals the square root of 2. So the intersection of the sphere and the cone is a circle of radius square root of 2. So in polar coordinates now, our r is going to go from 0 to the square root of 2. And again, we have pi going from, or theta going from 0 to 360 degrees, so 0 to 2 pi. So that's our setup here. We can integrate that in z. I'm not going to do the whole integral on very many of these videos from this point on, but we integrate this in z. R is a constant as far as z is concerned. So we get an r times z from r to the square root of 4 minus r squared. We still have our dr d theta. 0 to 2 pi, 0 to the square root of 2, r times the square root of 4 minus r squared minus r squared dr d theta. That's it. Now the theta integral, there's no theta dependency. We talked about this last time. There's no theta in here. So we know the theta integral is just going to contribute to 2 pi. So 2 pi times the integral from 0 to the square root of 2, r times the square root of 4 minus r squared dr. And finally, I'd like to break that up and leave it for you to finish. Break that up into two integrals. And the one integral here is just, one integral is the power rule, And the reason I broke it up is because this integral requires a u substitution. We have to use u equals 4 minus r squared to do that integral. So I'm going to leave at this point. We have a u substitution, we have the power rule, both things that we're comfortable with. And if you need help on a u substitution or power rule or any integration, you should reach out to me and let me know, and I will help you with those things. But I'm going to leave the video at this point.